Welcome back to the Explainer. All right, last time we built the absolute core of our CPU's brain, the arithmetic logic unit. And this thing is a beast. I mean, it's a brilliant piece of logic built from scratch that can add, subtract, and crunch through all sorts of logical operations like and, or, and not. It's basically the high-speed calculator at the heart of our machine. But here's the thing. An ALU all by itself is kind of like a brain in a jar. It's powerful, sure, but it's just a calculator sitting in the dark. So the big question for today is, how does it get instructions? Where does it store its results? And how in the world does it talk to anything outside of itself? It needs a nervous system, right? So let's get started and draw the map for that system. Okay, first up, a map for all our data. Now, you might think, hey, let's just run dedicated wires for everything. You know, a set of wires for instructions, another for data, another for turning on a light. But trust me, that would be an absolute nightmare to manage. The elegant solution, the smart way to do this, is to create one single unified system where every single component has its own unique address. Think of it exactly like a building directory in a huge office tower. Every single office, every apartment, has a unique number. You don't need a separate map for the mailroom and another for apartment 3B. You just look up their address. Well, we're doing the exact same thing in our computer. Every single memory location, every external port, it all gets its own address. And here it is. This is our computer's building directory, our memory map. This shows you exactly how we've laid everything out. And the most important thing to see here, the key takeaway, is that everything lives together in one big neighborhood. Our program memory, our temporary RAM, and even the ports that connect to the outside world, they all share one single 256-byte address space. Super clean. This amazing technique is called memory mapped I/O, and honestly, it is a total game changer. It makes the design so much simpler because our CPU doesn't need a bunch of special, complicated commands to talk to, say, an LED. Nope, it just writes a value to a memory address, like 0E0, the exact same way it would write to any other piece of memory. The hardware handles the rest. It's brilliant. All right, section 2, ROM, RAM, and I/O. So it's really crucial to get what each of these address ranges is for. Let's do a quick meet and greet with the residents of our memory map and see what they all do. First up, we've got ROM. That's read-only memory. Think of this as the computer's permanent instruction book. It's where the program itself, the actual list of commands for the CPU, is stored. And it's read-only for a very good reason, so the computer doesn't accidentally scribble over its own instructions while it's running. That would be bad. Next door is RAM, random access memory. This is our workspace, our temporary scratchpad. When the ALU adds two numbers, where does the result go? Right here, in RAM. Now, it is volatile, which just means it gets wiped clean when you turn the power off, but for all the in-the-moment calculations, it is absolutely essential. And finally, we have the I/O ports. I/O just stands for input-outputs. This is how our computer actually connects to reality. It's the CPU's senses and its voice. Through an input port, it can read whether a switch is flipped. Through an output port, it can turn on a motor or light up an LED. This is how our little digital brain can actually sense and affect the physical world. Okay, section 3, the code that directs traffic. So how does this actually work under the hood? I mean, when the CPU says, hey, I need to read from address 0x20, or I need to write to 0FF5, how does the system know where to go? Well, the secret sauce is baked right into the hardware's design, which we're describing using a special language called VHDL. Let's look at this line of code. This is our first traffic hop. It's looking at the most significant bit. That's the 8th bit of whatever address comes in. Now remember our memory map. Any address from 0x0 all the way to 0x7f has that bit set to 0. So if this little piece of logic sees a 0 in that spot, it knows instantly, this is for the ROM, and it passes the rest of the address along. And you guessed it, the opposite is also true. If that first bit is a 1, the request has to be for the upper half of our memory map, anywhere from 0x80 to 0xFF. And what lives up there? Our RAM and our I/O parts. So with this one simple check, we've basically split our entire memory space right down the middle. But we need to get even more specific, right? So to find the output ports, the code looks at the first 4 bits of the address. If they match the pattern for the hex value E, and hex is just a shorthand we use for binary, it knows that the address must be somewhere between 0xe0 and 0xef, and boom, it activates an output port. And for reading from the input ports, it's even more direct. This block of code is basically just a big switch statement. It says, okay, let me see the address. Is it exactly F0? Then give the CPU the data from input port 0. Is it FF1? Okay, give it the data from input port 1, and so on. This right here is memory-mapped I/O in action. It's beautiful. This whole process that we've just walked through has a name. It's called address decoding. All of those when-else statements in the code, they're just a really simple, super elegant way to build a digital traffic director right into the hardware, making sure every request goes to the right place. So in actual hardware terms, what does this VHDL code create? It synthesizes what's called a giant multiplexer, or a MUX for short. And you can think of the 8-bit address coming from the CPU as the selector knob on that MUX. Based on that address, the MUX physically creates a connection, telling the main data bus whether to listen to the ROM, the RAM, or one of those very specific I/O ports. All right, section 4, assembling the system. So let's pull the camera back a bit and see how all these pieces fit together to build our complete computer system. We're zooming out from the individual lines of code to the high-level architecture. And at the very highest level, our entire design is just beautifully simple. Seriously, as you can see in our top-level VHDL file, it's really just 2 main blocks: the CPU module we've been working on and our new memory module. And they're just connected by a few shared highways, or buses. One for the address, one for data coming in, one for data going out, and a simple signal that says, hey, are we reading or are we writing? And that's the real beauty of this whole setup. The CPU's job is actually made a lot easier. It doesn't have to know what's at address 0F0. It doesn't care if it's RAM or a sensor. It just knows it can read a value from that address. The memory system's address decoder does all the heavy listing, figuring out that, oh, 0F0, that's actually an external input port. Okay, section 5, the final missing piece. So let's just step back for a second and take a look at what we've actually accomplished. We have built some incredible, fundamental components here. I mean, think about it. We now have the 2 most fundamental parts of any computer ever made. We've got the part that thinks, that's our ALU, and we have the part that remembers and communicates. That's our brand new memory and I/O system. But here it is, the big question, and this is why this all matters so much. Right now, we have a silent orchestra. We have all the instruments, the ALU, the memory, and we even have the sheet music sitting there in the ROM. But who's the conductor? What's the spark that actually reads the instructions, tells the ALU to add these 2 numbers, and then tells the memory to store the result? What's running the whole show? That missing piece, that conductor for our digital orchestra, is the control unit. It is the final critical component of our processor, and it's the piece that brings everything else we've built roaring to life. So join us next time as we design the very last piece of our CPU puzzle.